Hello and welcome to my channel. About 1 month ago I released a video in which I was demoing the STM32 ecosystem, where I used a standard Eclipse install and I added the ARM toolchain. Now the problem with that was that a few things didn't work that smoothly. First of all, it was not too easy to install part of the toolchain, and also to configure all the tools. There is another way. It happens that early this week I was invited by ST to participate to an interesting workshop which was exactly on this topic. It's the STM32 programming ecosystem. So if you use the system workbench, which is still Eclipse, you can see it here, things become much easier. Basically, it is a version of Eclipse, Mars 2 in this case, which is already pre-packaged with all the plugins that you need. I will show you here. You see this AC6 symbol. If you go here, you see these are the plugins that come by default with this installation. So you don't need to separately set up the toolchain, the builders, and whatever, right? And trust me, it makes things much easier. So first of all, here you can see I'm using this board. This is a Nucleo 64 based on L4 processor. It is a Cortex M4 low power. And these boards, they come with an interface which is called ST-Link. You see there is a USB cable going in here, because this part is the ST-Link interface. Should you have a board that doesn't have an ST-Link interface, then normally you will have to use a JTAG, like I used J-Link. However, you can buy an ST-Link standalone in eBay for about $3 delivered, and it connects directly to pins on the processor. So if your board breaks out, normally you also have a breakout for the ST-Link, but if I don't, then you just use normal jumper cables and you connect to the pins that are breaking out in your board, and you should be all set. The advantage is that obviously it is much cheaper. Maybe it's not that powerful in terms of speed of uploading data, but for most of the application, I think you would not notice the difference. So basically, the other problem that was there when I used Eclipse and CubeMX is that I had to physically copy the project from Cube to Eclipse, and I used a Python script for that. But obviously that means that if you create a project with Cube, then you add your code and then you copy again the project from Cube, you will overwrite the code that you created. So there is a much better way, and this is what I'm going to show you today. So first of all, we start from Cube. We make a new project. Since I'm using a standard ST board, which is the Nucleo 64, I will select it from here instead of selecting the MCU. It's much faster. And I know this is an L4, and it is the first one. So I don't know if you already know CubeMX. If you saw my previous video, probably you have an idea, or if you use that. If not, maybe you can check. I will put the link in the description on the previous video, and then you can see eventually some more details about Cube. So the good thing is that since I selected the board, then it selected already the correct MCU, but also whatever is connected on the board to this MCU. You see, we have already set here a push button. Let me show you. It is this blue one here. It is connected to PC13, and there is an LED which is connected to PA5. I will do a very simple demo. I will use a timer to blink an LED, okay? But just to give you an idea of how Cube and the system workbench and the drivers cooperate, okay? So as I said, I want to use a timer to blink an LED, and basically in the STM32 has a bunch of timers, and they have, depending also on the family and the exact MCU that you're using, they have different functionality. Okay, they're extremely powerful, and they allow to generate PWM signals. They allow to be used as counters. They can be used to interface encoders like quadrature encoders with direction and all this kind of stuff. So timers, they might have, like, just select timer 1 for instance, different options and several channels that can be used as input or output, meaning that you can even cascade timers if you want, but you can have an external clock where the timer will act actually as a counter, and then you can also add an output that is going to be eventually a PWM signal or maybe a clock for something else, right? So since our application, the demo today is going to be extremely simple, I'm going to use a basic timer. Timer 6 and 7 are, I guess, for all the families, very basic timers that just do, you know, like an interrupt every third second. So I will use timer 6 in this example. And as you can see from here, it does have a lot of options less than timer 1. Okay. Plus, the good thing is that this will work for most of the other families as well. Then the other thing is clock configuration. This screen can be a bit scary. Setting up the clock is no joke, because there is a main clock. You can have different sources of this clock. You can have a PLL, you have a prescaler, and then you have a number of sub-clocks. So by default, when you use a board like the Nucleo 64, Cube is using the maximum available frequencies, which is 80 megahertz in my case. Okay. The good thing here is that, imagine I want to have 40 megahertz, then it's going to change. I just put 40 here, and it's going to change all the other parameters so that they match the frequency that I want. But just leave it at 80. It's going to be okay. Then configuration. Well, we need to configure something. Actually, we need to specify our timer. You want to control the timer. First of all, we want to enable the interrupt. We go to NVIC, which is the nested vector interrupt controller, and we enable the interrupt for this specific timer, right? Then we go here. Every timer has a prescaler and a counter period, at least. This one doesn't have a lot of options because I selected on purpose the simplest timer available on the processor, right? So the prescaler is basically a prescaler, meaning that it will divide the frequency of the input clock, which in this case is 80 megahertz, by the number that we specify here. If you specify 0, it's not dividing by 0, it's divided by 1. So that means that you have to put the value of the divider here minus 1. In this case, we want to generate a 2 kilohertz signal. So we will divide by 40,000, so we will specify 39,999. And then let's say that we want the period to be 1 second, so we blink the LED with a period of 1 second. Here what we do is we have a 2 kilohertz signal at this point. We still want to divide it by 2000 to get a 1 hertz period. So we divide by 2000, so we specify 1999. We apply, and we are done with the configuration. Now, this is something quite important. We need to go to code generation, right? But before generating the code, we want to set a few settings. This is an important one. Where I'm saving the project, it is not, and I repeat, it is not the workspace of my Eclipse installation. It's not the workspace of the system Workbench. Why so? Because basically what we want to do is we want to create the project in a folder. We want to create all the files needed and then import from that project. It doesn't mean that files will be copied by Eclipse into the workspace. They will be just linked. This is important because if you create the project directly in the workspace, you won't be able to import it because Eclipse will find a folder that already has the name of the project, and it says, I guess I already have a project with that name, so you won't be able to import it in your folder. So let's call it timer demo, for instance. And here we set a few things. Here we set the tool chain. In this case, we are going to use the system workbench, so select this option. Then here we leave it like this, we don't care. This one, we are not going to change it, but I want to show you. You see, you have for every peripheral, you can select which driver to use. We're going to use the hardware abstraction layer, which is the easiest driver to use, but there's also another options, which is the LL, means low level. If you're not an expert and you don't know what you're doing, just use HAL. It's much easier, right? LL is there, and it can be an extremely important resource for some of you guys. It's needed if you want the best performance possible and reduce the number of system calls, function calls, and stuff like that. However, it doesn't do all the things for you, right? So HAL will actually add a lot of code for you, while with the low level you will have to do many things manually. So in my case, for this demo at least, HAL is going to be a good option. So we are all set. We have a name. These parameters, they're set automatically when you set the processor, so normally you don't have to change them. So we say OK, and then what we do is we generate the code. It's now generating the code. Remember, it is in a folder that is specified on my drive, which is not the workspace of my Eclipse. Now we go to Eclipse. This is our workspace. Let's add the new project. We go File, Import. We select Existing Project into Workspace, and then we go here. It is on my drive C, and it is here. You see it's showing a few what was the timer demo timer? Now I'm lost, 1 second. Timer demo, okay. So these are already in my workspace, so I was not able to load them. So see, if I created basically a project, if I copied the file directly in my workspace, I wouldn't have been able to select it to import it in the workspace itself, right? Since this is a different folder than my workspace, then I can import the project. And there it is. This is our new project. So a few things that I learned during the workshop, maybe it's worth mentioning. You want to check here in the properties and the behavior, enable parallel build. It's a bit faster in compiling and building. And then the toolchain editor, this is what you expect to see. Okay, AC6, STM32, MCU, GCC. Normally, this is set by default and everything. If, like myself, you have maybe different version and different compilers and stuff installed, then you might have something different here. So make sure that this is your selection. And then the builder is the GNU Make builder. You can experiment also with other tools. Feel free to try. Here, the other thing that it's a good idea to do is enable specific settings for the indexer and remove this option, index source file not included in the build. Okay, that's because if not, you can get some errors from the indexer. No big deal, but just to avoid to waste time and have weird errors showing up. And then that's basically it. Actually, I need to do another thing, but I will show you later, because this is my second installation. This is on my main PC, and as I said, I have a lot of tools. So something goes wrong when I try to build, and I will show you how to fix it. I didn't have to do that on my laptop, but instead of fixing it right away, I want to show you the issue so that you can recognize if you have the same issue, and then you can apply the same fix. So here we have our code in source main. This is our code. And as you can see, CubeMX generated quite a lot of code for us. So first of all, in the main, it does init the HAL libraries, it configures the clock, and then it inits two of the peripherals that we selected. Is GPIO, you always need a GPIO, and the timer, right? But it does init them, but it doesn't start them. So this is something you have to do yourself, and I will show you in a few seconds. Just let me show you the error that I get when I try to build this one. So I go here and I go build project, and as you can see here, I do have this error 258. This is actually something a bit weird, and I don't really understand why, but I know the fix because I found it on the web. If you have something like this, like myself, you can go here, and then you go in the C++ build, you go to settings, and then you select symbols, and you see those two that are used during the build process. So you add single quotes, beginning, end, like this. Didn't have to do it on my other installation, so I bet because I have different versions of different stuff, but that normally fixes the problem. So here, let me clear this one. Now that I did that, I can maybe clean, what is it? Clean, and then build. As you can see now, it didn't stop, it's going ahead and it's compiling and building my project. So it finished, it worked, it took 5 seconds or something. So obviously it doesn't do anything, but just let's try to load it, but obviously it won't do anything because we didn't add any code, right? It is only initialization. So I go to debug, it opens the debug interface. As you can see, this is my board, still not doing anything. This blinking here is the ST-Link that is sending and receiving information, right? So I can run my code. It's now running, but again, since we didn't add any functionality, it's not doing anything, right? It didn't even start the timer actually. So let's do that. Let's stop it. We go back to the C++ perspective, and then here what we want to do is we add here we want to start our timer. You see those comments, don't remove them. User code begin to, user code end to. Here we are in the main function of the main.c, and this is before the infinite loop. So this is the end of the initialization phase if you want. So here is where we start our peripherals, in this case the timer. We use HAL underscore timer tim underscore base underscore start. I just do st and then control space, and then you see I have start DMA, start IT. So the reason is if you use start, then it's going to be the polling version, right? So there's going to be no interrupt, there's going to be no DMA. We will just have to poll the counter, which is not what we want. This one will enable the DMA, which we would have configured before in the cube. And this one will eventually enable the interrupt, which is what actually we want. So here it's expecting the handler. The init function, this mx timer 6 init, is going to create, actually is going to populate this thing which is called the structure STM6. That's the handler, okay? So, and this is the parameter that it is expecting here. STM6 there. So with this we start the timer. What happens is we still need to normally this is going to generate an interrupt. We don't need to create the ERQ service function because this is already managed by HAL. Actually this function is calling a callback function. And we can override, and we will override indeed, that callback function. Okay? So where do we do it? Obviously outside of the main, and you see here user code begin 0, user code end 0. That's a good place where to put this function. So it's very simple, but just let me copy paste it so that I don't mistype. There. Be absolutely careful where you put things. It wouldn't work. Well, it would compile, it would work, but then I'll show you we would have problems if we put something here. So basically what I do here, this callback function, it's taking as a parameter the handler. That means that there is not a specific callback function for every timer. There is a callback function for all the timers. So the first thing we do is we check that if the instance of the handler, timer handler, is the one that we expect, like timer 6. And then in this case we toggle our pin using HAL again. It's A5, so GPIO is the A is the port, and GPIO pin 5 is our pin. And that's basically it. We finished. So we just build it again. And also, when you have more than one project, you may end up debugging the wrong one. So a good thing is you just go here, you go like debug as AC6 STM32 C++ application. Now let me show. Now it compiled, it loaded whatever is needed on the board, but obviously we didn't start the code yet, so there's no blinking, right? So let's start and then go back to the. Did I start it? Nope. Now yes. What is it? No, something wrong. Where is it? I guess I didn't. Yeah, that's another issue that you can have. You go to debug configuration. Much better, yes. And this is gonna be timer demo alpha. Seems to be correct. Debug. Loaded. Oh, there it is. You see the LED is blinking with the period that we specified here. Let me center a bit better. This one. So basically we just created a few lines of code, and we added the functionality on top of what was created by the cube. However, we defined the period in cube itself. So what if we need to change the period? Well, there are different options, but I'll show you the correct and the less correct way of doing it. One thing is, if we go here in the init, you will see that here you can find the parameters that we did specify in a cube. So obviously if I change those parameters, that will change the frequency. However, this is not the part of the code that the user is supposed to change. Why? Because this part of code is the one that normally is managed by cube. So it means that we can go back to our cube project here and change this one, like make it much faster, like 4 times faster, 499. Apply. And then we regenerate the code. Now, obviously we did add some code, but Cube is smart enough to read back the source, identify those sections that we did add, regenerate the code, and repaste in the sections that we actually added, provided that we added the code in the correct place. So you see now, here the parameter automatically changed. That was managed by Cube. However, if we go down, sorry, it was up. This is the code that we added. It was not removed, still there. So again, if we build the project, build project. And then we debug it. Debug is, let me check if it is the correct one. Timer demo, yes. Debug. Yes, a switch, please. So now it's not doing anything because the code is not running. If I start the code and then go back here, you see now the frequency of the LED is much higher. So long story short, if you do it the proper way, you save a lot of time and a lot of effort, and you avoid to do a lot of mistakes. Thanks for watching.